Hello everyone, I'm Shen Sheng from Tianjin University, and today I'm excited to present our work on Dec-Adapter, a pioneering approach for efficiently bridging screen content and natural image compression. This work tackles the challenges in cross-domain image compression, particularly focusing on screen content and natural images. Let's dive in. Before diving into our solution, let's talk about why this research is important. First, as we all know, there is an ever-increasing demand for high-resolution images and videos for online consumption. Traditional codecs like JPEG and BPG are quickly being surpassed by learning-based image compression approaches. However, these models, while effective, have their limitations. We encounter a significant degradation in compression performance when applying these pre-trained LIC models directly to screen content images since they are two different domains. Fine-tuning these models for a new domain not only consumes valuable resources but also reduces their generalizability. In addition, we also face domain shift issues between training and testing phases. So, how do we solve these challenges? This brings me to our contribution. Our primary contribution is the Dec-Adapter, which stands for Decoder-Side adapter. We introduce the concept of entropy-efficient transfer learning specifically for screen content image compression. Our Dec-Adapter is a lightweight, domain-transferable, and architecture-agnostic module. Through extensive experiments, we have demonstrated a significant improvement over existing methods, including an over 2 dB gain compared to the baseline when transferred to screen content image compression. Let's delve deeper into how we achieve this remarkable performance. Our methodology builds upon the widely used variational autoencoder architecture that serves as the backbone for most learning-based image compression models. We introduce Dec-Adapter into this established framework to tackle domain-specific challenges. Let's take a closer look at how Dec-Adapter fits into this scheme. We propose Dec-Adapter to handle the degradation of performance when compressing out-of-domain images. It's an entropy-efficient adapter designed to be integrated within the res blocks on the decoder side of the model. Dec-Adapter utilizes a simple yet effective bottleneck structure, which includes 2 convolutional layers cascaded by a GELU activation function. The architecture is designed to be lightweight yet capable of performing domain-specific adjustments efficiently. We provide 4 different schemes for adapting a res block in the decoder. The Dec-Adapter can be flexibly inserted into every res block to adjust features at different depths. Our model optimization has 2 stages: latent refinement and decoder adaptation. In latent refinement, we fine-tune the image's latent representation for optimal compression. We use an optimization strategy focused on minimizing rate distortion, executed via a local decoder on the sender's side. This way, we can tailor the model to the image without extra bit cost. In decoder adaptation, after refining the image's latent representation, we fine-tune the Dec-Adapter. We employ a mixed quantization method and a loss function aimed at rate distortion, this time also considering the Dec-Adapter's parameters. These are then quantized for decoding. We've packaged these stages into a single algorithm, balancing efficiency and performance, which is displayed on screen. We dive into the experiments conducted to demonstrate Dec-Adapter's domain transfer capabilities and overall performance. We used Kodak, SCID, SIQAD, and CCT as our benchmark datasets. Cheng 2020 serves as our backbone model, which was trained using natural images. We have benchmark datasets with natural and screen content domains. For instance, Kodak focuses on natural images, while the others are screen content datasets. These datasets vary in terms of average resolution and test number. To measure the performance, we used metrics like PSNR, BPP, and BD rate. We employed the ADAM optimizer for training. Specifically, we ran 2,500 iterations for the latent refinement and 500 iterations for adapter training. The learning rate was set at 1E3 for the first 80% of the iterations and dropped to 1E4 for the remaining 20%. We also conducted a comprehensive comparison of our method with existing state-of-the-art adaptive compression techniques. We used the Bjontegard delta bit rate or BD rate as our evaluation metric. What's notable is that our method performed exceptionally well on both in-domain and out-of-domain datasets. This shows the versatility and effectiveness of our approach, especially when applied to diverse image types. We compare our method with the baseline that does not use adaptive optimization. We calculate PSNR and BPP for each image and plot the average values on a rate distortion curve, as shown in Figure 4. Our method outperforms the baseline by 2 dB when adapted to the screen content images, which verifies the effectiveness of our adaptation performance for bridging natural and screen content compression. In the ablation study, we first focused on the role of adapting variants. We tried 4 different variants and found that serial conv performed the best in terms of BD rate, particularly when connected at location 2 of our architecture. This finding was crucial in optimizing our final model. Furthermore, we investigated the impact of the DW-conv kernel size and the channel squeeze factor. We found the best performance at a DW-conv kernel size of 3 and the bottleneck layer dimension of 16. These insights helped us fine-tune Dec-Adapter. We also wanted to find out whether applying adapters to only the later layers of the network would suffice. Surprisingly, it did. Attaching adapters only to the last block led to over 20% in BD rate savings. This not only improves efficiency but also keeps the computational cost low.